Continuing on with the class 1 videos, I think this is video 4 maybe. We're going to get into section 1.6 where we talk about the specific volume and density, an important property in thermodynamics. So we're going to use a lowercase v, and often with a little bit of italicized. I usually go like this right here. I have been taking a habit, I don't know if I'll always be consistent, where I take volume as capital V with a line through it, because there's too many V's in there. So this V, and sometimes I might even take specific volume, by the way, and be like this, but of course that looks like actually a mu, or is it a nu? I can't remember, one of those. But anyway, we're taking volume and dividing it by mass. So we're saying volume on a per mass basis, which if you turn it around right here is, mass divided by volume, that's density, right? So just recognize that density and specific volume are just the inverse of each other. You can see on the range of things how small the specific volume of gases are. Well, of course, they are very hot. Let's see, I'm going to say that. No, that's density. Well, duh. All right, so it's the opposite way, right? Gases have very high specific volume, where they have a very low density, and solids can have a very varying density right there. Some things are going to be less dense, and therefore they will float, right? So that's usually a comparison of densities will decide whether something floats or does not float, and if something is floating, I should point that out somewhere in here, right? Maybe. We'll say that in a minute. And you can see that lead will be often denser than water, and of course it will sink. So density is really mass per volume. And specific volume is volume per mass. And as I alluded to in the intensive and extensive properties, that for us is often a thing that we like. We like things on a per mass basis. So this is in keeping with the way we will be approaching much of the heat and the work and the entropy of thermodynamics. And this usually has a lowercase letter. Specific gravity is a way to express the relative density, if you will. So you go relative density to standard water. Here can be standard is STD, and then water, WTR. Saved myself a couple letters, didn't I? And it's like standard water because it's a standard, like a standard temperature water that we use. So it's density over density. So it is a unitless and dimensionless is a better word for it. Dimensionless parameter, and it is often called SG, right? Specific gravity. So that's like a depart from what we call specific right here. And here's another departure from what I mentioned as specific. A lot of times I think of as specific as being on a per mass basis, but usually it just kind of means that we've divided it by something. So specific gravity is, if you want to find the density of something, multiply this value by the density of water and you will get it. So it's like a shorthand thing, but it's also kind of like a ratio. Anything greater than 1 of a specific gravity means the thing is going to sink. Anything less than means that it's less dense than water and therefore will float, right? Specific weight is really just density times gravity. But it's also, you can think of it, is the weight per volume, aka weight per volume. There's no room for this right here, but really important dude. Trying to remember his name now. Boy, I'm losing it. I'm gonna have to look it up here in a second. I'm gonna have to end this and look up. Should I Should I pause this and look up? Is it Archimedes? I think it's Archimedes. Yeah, Archimedes made a really important discovery, and that is if something floats. Let me see. I'll write it right here. If it floats, so we got something that floats right here. This guy right here, that this little section right there, so the weight of the water, the weight of fluid will equal the weight of the thing, right? So if you have a ship and it's floating, all you have to do is figure out what the volume of the region that's below the water, figure out that volume, and multiply it by the weight of that volume. So what I often will do is we'll look up the specific weight, that's the weight per volume, and multiply that times the volume. And you'll be able to estimate or just measure. That's how much it is. So if it's floating in water and it's, whatever volume that you were able to measure, it's usually easy to measure something that's a rectangular thing as opposed to something that's got some kind of shape to it. Just, calculate the length times the width times the depth and multiply that by the specific weight, and now you know how much the thing weighs. It's almost like a scale, and as long as you can figure out the volume, you can measure the weight. So here's some stuff out of the Appendix 1, where we have the equivalent of density we could find in the pounds mass per cubic foot. They didn't bother with the slugs for some reason. I don't know why. Don't ask me why. I think we can probably look that up in the other section there, or we can figure out. We can do the pounds mass into slugs, I guess, but we're not going to be using slugs all that much right here. But do we actually have mass in a slug? There you go. We could use this slug, although they don't have. Yeah, they didn't make this really useful to us, did they? Yeah, I'm criticizing the book. But whatever. So forget about slugs for now, but you'll need it later in dynamics. And the other different things, they don't have, there's actually, I think gallons and cubic feet is actually a really useful. They have cubic inches, gallon and cubic inches. And is there different a UK and a US gallon? Is there a difference? I don't know. I'm feeling good about that. Anyway, specific volume. So here you go, looking up for conversion factors. Do I want to do the example or make it a new? Oh, it's an 8-minute long video. Let's do the example in the next video. Talk to you soon.